Welcome to Material Innovation Forum, the podcast exploring the profound intersection of material science, chemistry, and sustainable energy systems. I'm your host, Rittika, and today we are privileged to speak with Dr. Sibo Chetry, a postdoctoral researcher in Germany, whose expertise spans advanced material for environmental and energy challenges. With a focus on bridging fundamental research and industrial application, Dr. Chetry's work aligns closely with Germany's ambitious sustainability goals. Dr. Chetry, thank you for joining us to discuss these pivotal topics today.
Yeah, thank you, Ritika. It's an honor to engage in this dialogue, particularly as Germany acceleration its energy vendor, where the materials innovation play a central role in achieving net zero targets.
Right. So our discussions will cover four rather interconnected areas: CCUs within the German Mittelstand, advanced porosity characterization, the hydrogen material roadmaps, and circular chemistry principles. These themes are essential for academic and industrial leader navigating the complexities of scalable, sustainable technologies. Let's start with CCUs, carbon capture, utilization, and storage in the German Mittelstand, the SMEs that drive much of the economy's innovation. Dr. Chetri, how are material advancements facilitating scalable carbon dioxide capture in this sector?
Yeah, Ritika, first of all, thank you so much for the beautiful question. And well, the Mittelstand involvement in CCUS is critical, as this enterprise often specialize in sectors like cements and chemicals, so where the emissions are hard to abate. Recent policy shifts, such as German cabinet approval in August 2024 for infrastructures reform, enable CO2 transport and the offshore storage, which has already been started, have opened a pathway for SMEs to integrate CCUS without prohibitive costs. In my postdoctoral research, I have explored solid sorbent like amine functional um, porous materials which offer regeneration energy as low as 2 gigajoule per ton of CO2 compared to 3 to 4 gigajoule for liquid amine. And this is particularly relevant for Mittelstand firm in Ruhr Valley, where the project like Heidelberg Material commitment to capture net zero um, carbon capture net zero concrete by 2050 demonstrate a practical implementations. And notable examples is Holcim's Carbon 2 business projects in Lägerdorf launched in April 2024, which captures CO2 from cement production for utilization in value-added products. Here, the Material Innovation Center on hybrid material, combining metal organic frameworks with ionic liquid to achieve uh, really high flue gas selectivity, exceeding 150 under flue gas condition. And this challenges for scalability lies in impurity tolerance, particularly for SOX and NOx, can degrade sorbent by 20 to 30% over cycles. My work or my new projects involve on computational screening by density functional theory to design robust frameworks. Also look for the reducing degradations of this kind of MOF under 5% and aligning with the Copernicus project emphasis on earth abundant catalyst for CO2 conversion to value-added products like methanol or formic acids with a Faradic efficiency of above 85%.
So, the integration of policy and material science is pretty evident to me. How does this extend to utilization pathways that create economic value for SME?
Well, utilization transforms CCUS from cost center to revenue stream. In Germany, the global CCUS absorption market is projected to grow from USD 0.4 billion in 2024 to 1.7 billion USD by 2030, driven by innovation in electrocatalysis for Mittelstand breweries or the biogas plants. Captured CO2 can feed into photocatalytic reactor using materials like bismuth vanadate, yielding ethylenes with efficiency up to 10% under mild condition or ambient conditions. Life cycle assessments are key. So, ensuring the net CO2 reduction exceeded 90% require regenerable catalysts such as copper-based electrodes with over potential below 300 millivolt. Media discourse analysis from 2024 highlights public perception challenge for CCU, emphasizing the needs for transparent life cycle based metric to build a trust.
So basically, transitioning to decoding porosity, advanced characterization tool for functional material under real conditions. So porosity governs performance in catalysis and storage, yet dynamic assessment is complex. What techniques are you leveraging over here?
Basically, porosity characterization must account for operational realities, temperature gradient, mechanical stress, and chemical fluxes. The statics methods like BET overlook in recent advancement operate to synchrotron X-ray scattering at facilities like DAISY or in Berlin or Vetra 3 in Hamburg reveal poor evolution in real time, showing the collapse in GeO2, in zeolites under CO2 loading with the hysteresis loop up to 15% volume change. A 2024 studies on accurate pore volumes in microporous crystal introduced pore accessible matrix using positron annihilation spectroscopy, which was conducted by SCDR with some of the researchers like Ahmed, who were working extensively with these techniques and quantifying the defects at angstrom scale under mild environments where the water reduces the effective porosity by 25%. For energy materials, solid state NMRs map into dynamics in porous electrolytes, also including this 129 xenon NMR spectroscopy as well. Identify this toxicity factor that limit the conductivity in solid state batteries to 10 to the power minus 4 Siemens per centimeter. Integrating this with the micro CT tomography and AI-driven analysis as an autonomous research workflow from 2025 works of enabling predictive modeling of failure modes. And scale-up challenge highlight in a 2024 Nature Communication review include a maintained consistency in MOF shaping by a 3D printer or template-assisted method, ensuring the porosity retention above 80% post processing. My contribution in near future involves couplings, this neutron scatterings with molecular dynamics to decode this hydrogen bondings or the mechanism behind this to biomimics the porous structures, um, enhancing selectivity for clean tech applications. Yeah.
Okay. So, this multi scale approach is very compelling. How do these tools inform sustainable energy materials?
Well, in perovskite solar cells, SEM and interfacial engineering reveal porosity role in the stabilities. With the nanostructured layers reducing degradation by 40%. Let's take an example. For example, hydrogen storage Operento techniques tracks hydride formation in magnesium-based alloy, optimizing kinetics via doping to diffusion coefficient of 10 to the power minus 7 centimeters square per second. And this ties into broader structuring strategies for MOFs and COFs in energy application, as outlined in RSC paper review by 2025. emphasizing the hierarchical porosity for mass transport. Yeah.
Right. So let's talk about the hydrogen material roadmap, right? So, engineering for storage, transport, and infrastructure. Germany's national hydrogen strategy is evolving rapidly. What are the core material challenges?
I think the update based on 2024 to the National Hydrogen Strategy target linking major production, imports, and the storage site by 2032 via expanded infrastructure, building on 2024 standardization roadmap for technologies like pipelines and storage. Storage material focus on LOHC like perhydrobenzyl toluene, achieving density of 57 kilogram meter cubes with the dehydrogenation at 280 degrees centigrade using ruthenium-based catalysts. But the alternative like molybdenum disulfide reduce cost by 50%. And improvement in the transport pipeline. This X70 steel degradation under 20 bar H2 necessitates liner with the carbon nanotubes extending service life per ISO standard. The IEA's Germany 2025 report underscores a sectoral roadmap for electrification supported by hydrogens, aiming for 10 gigawatts electrolyzer capacity by 2030 in trans-HYDE projects. Materials for liquid hydrogen transport include insulating composite with boil-off rate below 0.5% per day. So based on the studies, which what I knew, and the research optimization, hydride dopant, improving reversibility in LNAs for infrastructure scale storage with the capacity targeting 5 to 8% of H2 storage capability.
Right. So, how does this roadmap integrate with energy systems exactly?
So the sector coupling is vital. So PEM electrolyzer with porous transport layer minimize the overpotential to 50 millivolt which was determined by impedance spectroscopy. The Hydrogen Infrastructure Report 2024 project shows that 45 percent of hydrogen need by 2030, emphasizing repurposed gas grid. So the Germany storage roadmap position underground carbon for seasonal buffering with the material ensuring the seal integrity against the S2 permeation.
Finally, circular chemistry, designing recyclable and regenerable materials for clean tech. On this topic, with the EU's Circular Economy Action Plan, Germany is actually leading. So, what principles underpin your design?
I think the circular chemistry emphasizes atoms economy and the cradle to cradle life cycles. The National Circular Economy Strategy, adopted in 2025 with the circularity made in Germany, still promotes renewable materials and recycling targets. In clean tech, bio-based polymer like PLA derivatives from avonics replace PVDF in membrane regenerable via enzymatic hydrolysis with 95% recovery. For photovoltaic lead-free perovskite with tin achieve 18% efficiency and recyclability through solvent extraction. Chemical recycling, as in LYB's Wesseling plant from 2024, convert plastic to monomer via pyrolysis, feeding into clean tech feedstocks. Metrics like EROI above 15 guided design in BSF and Evonik greener polymers, CO2 based polyols reduce the fossil dependency by 30%, which is a big number. And my based on knowledge on regenerable solvent for CCUS uses covalent organic frameworks with 2000 cycles, stability aligning with the Boreas 2024 circular breakthroughs.
So these interconnections, porosities enable CCU's hydrogen infrastructure demanding circularity are profound. Any final reflections?
Indeed, they form a cohesive framework for sustainability. In Germany, hubs like Circular Valley foster collaboration, and I'm committed to advancing this to the future rules here in Germany.
Thank you, Dr. Chetri, for this rigorous explanation and exploration. Listeners, join us next for more.
Thank you.